this section, we will be working with some equations that are quadratics and others that are perhaps not quadratics, but rather quadratic in form. If the equation is quadratic in form, we will be able to identify a pattern. Due to this pattern, we'll be able to make a substitution to force a quadratic. We'll use methods then that we've discussed earlier in this chapter to solve quadratic equations. Our last step will be to substitute back to get back to our original variable. For our first problem, we begin by clearing the denominator. Since our denominators are prime, the LCD needs to be a product of both of the factors. Make sure that you are multiplying all terms by the LCD. With the first term, x minus 2 cancels, leaving you with x plus 2 and the factor of 5 that was there to begin with. Second term, x plus 2 cancels, leaving you with x minus 2 times 4, and over on the right-hand side, nothing will cancel. Next step is to free up all the terms by distributing. Since the degree of this equation is 2, we need to set this equation equal to 0. I will move all terms to the right to keep the leading coefficient positive. I wanted to know if this equation was factorable before going through the trial and error method of factoring. As you can see, I am checking the discriminant for factorability. Since the discriminant is not a perfect square, this quadratic is not factorable, and therefore we will use the quadratic formula to come up with our solutions. This equation is not quadratic. It's a fourth degree polynomial. In order to be able to be quadratic in form, there will be 3 terms. Last term is a constant. The middle variable squared needs to give us the first variable. If x squared is squared, the result is the first variable term, x to the 4th. Because this equation is quadratic in form, we will be able to make a substitution that will result in a quadratic. As long as we substitute back to the original variable, there is no problem in doing a substitution. The advantage will be that once we have a quadratic after the substitution, we can use the methods discussed in this chapter to solve. To determine what to use for the substitution, always focus on the middle variable. If you let u equal x squared, then the square of this statement will always give us the substitution for the first variable term. When both sides of u equals x squared get squared, x to the 4th gets a substitution of u squared. Because this equation is quadratic in form, after the substitution, we have a quadratic. U is typically the letter or variable that we use for our substitution variable. Any variable can be used, just make sure it is different from the original variable so that you're reminded to substitute back to get back to the original variable. This equation is factorable. We factor and we end up with u equals 11 or u equals 1. Again, we need to go back to our original substitution to get back to that original variable. Now substituting x squared in for x, we now have x squared equal to 11 and x squared equal to 1. Solve these by square rooting. And again, don't forget your plus or minus when you use the square root property. The degree of our original equation is 4, and we ended up with 4 unique solutions. Here's another example that is not quadratic, but it is quadratic in form. If you square the middle variable, the square root of x gives us x, the first variable. Since quadratic in form, we will be able to make a substitution that gives us a quadratic. To determine what to set u equal to, always go to the middle variable term. We will let u equal the square root of x. Because the square root of x squared is x, when we square both sides of our substitution statement, we have a substitution for the first variable. Solve the resulting equation by factoring, and you get u equals 2 or negative 1. Again, we are solving for x, not u. Therefore, we need to substitute back to get this back in terms of x. We end up with the square root of x equals 2 or negative 1. To solve these equations, we need to square both sides. We potentially end up with x equals 4 or 1. I say potentially since we are solving an even root radical equation. There is always the potential for extraneous solutions. These are apparent solutions that when substituted back into the original equation don't check and therefore need to be eliminated. On this slide, we are performing the check to find out only the 4 checks. Therefore, our solution is 4 since 1 needs to be eliminated. We finish with a word problem. This is a work rate application. With work rate applications, we will build our equation that will allow us to solve by using rate times time equals part. Let's first define the parts to this formula. Rate is defined to be 1 over the time that it takes a person or machine to do the job alone. Time is defined to be the time it takes when the people or machines work together. When we multiply these two together, we have a product that represents the part or percentage that one does when they work together. We will add these products together and always set them equal to 1. Across the top of the table is the formula rate times time equals part. In this particular example, we have 2 pipes. The large pipe takes 2 hours less time than the small when they are working together. Notice the rates. The large pipe is 1 over x minus 2 and the small pipe is 1 over x. Their time to fill the tank when working together is 3 hours. Therefore, 3 goes in for the time for both of the pipes. Multiply across for the part. When we add the parts and set them equal to 1, the 1 represents the entire task, 100% completed. That's one way to interpret this. Since this is a rational equation, we begin by multiplying by the LCD. Since our denominators are prime, our LCD needs to be a product of both. After multiplying through by the LCD and then distributing, we have a quadratic equation. Again, we set these equal to 0. To keep leading coefficient positive, move all terms to the right-hand side. Since this quadratic equation is not factorable, we turn to the quadratic formula. After approximating our solutions, we end up with 7.2 and 0.84 hours. X represents the time it takes for the small pipe to fill the tank. Does it make sense that there should be 2 possible answers? If the small tank takes 7.2 hours, the large tank would take 5.2 hours. If the small tank takes 84 hundredths of an hour, the large tank takes 2 hours less than that, which would give you a negative amount of time. And it doesn't make sense, of course, to talk about a negative time. Therefore, the 84 hundredths of an hour gets thrown out. This slide summarizes the solutions complete with units. Thank you for listening.